Imagine you could time travel right back to the very first second of the universe's existence. I'm not talking just any second here. I mean the absolute first second, when everything we know today, every single atom, every star, every galaxy, was squished into a spot smaller than the tip of a needle with temps in the trillions of degrees. But here's the mind blower. Even with all our tech, even with the most powerful telescopes ever built, there is a fundamental wall that keeps us from seeing those initial moments of the universe. It's like the cosmos has this impenetrable veil, guarding its deepest secrets. Today, cosmic explorers, we dive deep into this mystery that totally challenges how we get reality. The Planck Era and the first second of the universe, where the physics we know just breaks down. In this video, you find out why there is a hard limit to how far back we can look into the universe's past, how quantum physics and relativity get into an epic showdown in the very first moments of creation, and we'll check out revolutionary theories like loop quantum gravity that are trying to crack these mysteries. Get ready for a revelation that's going to completely flip your view on time, space, and reality itself. Welcome to Cosmic Frontiers. I'm your guide on this incredible journey through the universe's mysteries, and we rebuild in a community together that is super passionate about exploring the cosmos. Our crew of cosmic explorers is growing, and our goal is to hit 1,000 subscribers on this adventure of discovery that is just getting started. Now, close your eyes for a sec and try to picture absolute nothing. Not darkness, because darkness is still something. It's just no light, but there's still space. I'm talking about real nothing. No space, no time, no matter, no energy. Tough, right? Our brains just can't wrap around that idea. But here's where the story gets real interesting. We can never actually see the Big Bang itself. Know why? Because for the first 380,000 years of the universe, everything was so hot and dense that light couldn't even travel freely. It was like trying to see through an infinitely thick cloud. Light just got stuck, bouncing between particles in a chaotic dance. Only when the universe cooled down enough for the first atoms to form did light finally manage to break free. That first light that got loose is what we call the cosmic microwave background radiation. It's literally the first photo of the universe we've ever been able to snag. Imagine you're trying to watch a movie, but the first 10 minutes are completely covered by an impenetrable fog. That's exactly what our view of the early universe is like. And if 380,000 years already feels like an almost impossible barrier, just imagine trying to figure out what happened in the first second, the first millisecond, the first trillionths of a second of existence. This is where we hit one of the most mind-blowing and frustrating concepts in modern physics, the Planck Era. Max Planck, the German physicist who totally changed how we understand matter and energy back in the early 20th century, kinda accidentally set a fundamental boundary for human knowledge. The Planck Era is the first 10 to the power of -43 seconds of the universe, a number so tiny that if you wrote a 0 followed by 42 zeros before putting a 1, you'd still be dealing with that microscopic time slice. To get how ridiculously small this interval is, let's do a comparison that's literally blow your mind. If you compared 1 second to the entire age of the universe, almost 14 billion years, the Planck Era would be proportionally smaller than 1 second compared to trillions of universe ages. It's a scale so minuscule it defies any analogy we could ever cook up. But why is this period so special and mysterious? The answer is in the fundamental nature of reality. During the Planck Era, the universe was so small, so dense, and so energetic that the very laws of physics we know today just didn't work. It was a realm where gravity, the force that keeps our feet on the ground and controls the planet's movement, behaved in a completely quantum way, following the weird and counterintuitive rules of the subatomic world. Think of it like this. Imagine you're driven a car, and suddenly, the laws of physics change. The brakes start making the car speed up, the steering wheel controls the radio, and hitting the gas makes you fly. It'd be impossible to predict what had happened next, right? That is exactly what happens when we try to apply our current physics theories to the Planck Era. The equations that perfectly describe how matter and energy act at any other point in cosmic history just collapse and start churning out infinite, impossible results. During this mind-boggling period, it's believed that all the fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force were unified into a single superforce. It was like the universe was a symphony played by an orchestra with just one instrument, before it split into the four distinct instruments we know today. Albert Einstein spent the last 30 years of his life trying to find a theory of everything that could reunite these forces, but he never pulled it off. The holy grail of modern physics is still that very unification, a theory that could tell us what really went down during the Planck Era. Now, let's embark on a fascinating trip through the first second of the universe, moment by moment. Imagine you've got a time machine with a super precise stopwatch, and you watch in reality being born in super slow motion. We start at Planck time, 10 to the power of minus 43 seconds. At this moment, the entire universe was the size of 10 to the power of minus 35 meters. That is billions of trillions of trillions of trillions of times smaller than a proton. The temperature was an insane 10 to the power of 32 Kelvin. Just to give you an idea of that absurd temperature, the sun's core is only 15 million degrees. We talk in something trillions of trillions of trillions of trillions of times hotter than anything we've ever measured in the current universe. Moving forward to 10 to the power of minus 36 seconds, something extraordinary happens. The force of gravity separates from the other three fundamental forces. From that moment on, gravity starts following its own rules, which are the rules of Einstein's general relativity. But the real magic happens between 10 to the power of minus 36 and 10 to the power of minus 32 seconds, in a period cosmologists call cosmic inflation. During these few trillionths of a second, the universe went through an absolutely unbelievable exponential expansion. To get this expansion, imagine a grain of sand that suddenly grows to the size of a soccer ball, then the size of Earth, then the size of the solar system, all in less time than it takes light to cross a proton. The theory of cosmic inflation, proposed by Alan Guth in 1980, explains some of the biggest mysteries about why the universe is the way it is today. Know why the universe looks so smooth when we gaze at the night sky. Why the cosmic background radiation has pretty much the same temperature in all directions. Inflation's the answer. During this fantastic expansion, regions that were super close and in thermal equilibrium got stretched out to enormous distances, keeping their uniform characteristics. It's like taking a small photo and stretching it until it becomes a giant billboard. The pixels get spread out, but they keep the same info. Regions of the universe that are billions of light years apart today were once so close they could talk to each other and reach thermal equilibrium. Continuing our time trip, we hit 10 to the power of minus 12 seconds. We are still in the first trillionth part of the first second. At this point, the electroweak force splits into the electromagnetic force and the weak nuclear force. Now we've got three distinct forces working in the universe: gravity, electromagnetic force, and a force that includes both the strong and weak nuclear forces. It's wild to see how the universe just keeps getting more complex and interesting as it cools and expands. The early universe was super simple, a uniform soup of pure energy. But as the temperature drops, that simplicity gives way to the richness and diversity we see today. At 10 to the power of minus 6 seconds, now we're getting into the microsecond realm. The strong nuclear force finally separates from the weak nuclear force. Now we've got all four fundamental forces we know today working independently: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. The universe now has all the tools it needs to build the complexity we see all around us. Between 1 and 3 minutes after the Big Bang, something happened that completely changed the universe's destiny: Big Bang nucleosynthesis. During those few precious minutes, the temperature and density were just right for protons and neutrons to combine and form the first atomic nuclei. It's during this period that practically all the hydrogen and helium atoms in the universe were born, the elements that would later become fuel for the first stars. Think about it. In just 3 minutes, the universe cranked out enough material to power trillions of stars for billions of years. And then that window of opportunity slammed shut forever. The universe had cooled too much to keep making new light elements. But now we get to the point where our discussion gets even more fascinating and challenging. The boundary where quantum physics and relativity clash. For decades, these two theories, which are the pillars of modern physics, lived in a kind of non-aggression pact. Einstein's general relativity magnificently explains how gravity behaves on big scales. Planets, stars, galaxies, black holes. Quantum physics, on the other hand, perfectly describes the microscopic world: atoms, electrons, subatomic particles. The problem is, these two theories are fundamentally incompatible. It's like trying to use two different maps to navigate the same city. One map might show you should turn right, while the other insists you should turn left. Most of the time, this ain't a problem because we rarely need to apply both theories to the same object. But during the Planck era, the universe was simultaneously tiny, demanding quantum physics, and extremely massive, demanding general relativity. To get this incompatibility, let's think of an analogy. Imagine you're trying to predict how a raindrop will act. If the drop is big, you can use the laws of classical aerodynamics. It'll fall following a predictable path, influenced by wind and gravity. But if the drop is super tiny, the size of a molecule, it starts behaving according to quantum laws, following multiple paths at once, existing in several places at the same time until it's observed. Now imagine an impossible situation, a drop that's simultaneously gigantic and microscopic. What laws would it follow? That's exactly the paradox we face when trying to understand the Planck era. The early universe was so small it should obey quantum laws, but so massive that gravity can't be ignored. Einstein hated the probabilistic nature of quantum physics. His famous line, "Lord does not play dice with the universe," reflected his resistance to the idea that fundamental reality was uncertain and probabilistic. He believed there had to be a deeper theory, a theory of everything that could explain both the behavior of particles and the behavior of gravity in a deterministic and elegant way. But the decades that followed proved that the quantum nature of reality isn't just some mathematical quirk. It's a fundamental feature of the universe. And during the Planck era, when space-time itself had quantum dimensions, even gravity should behave in a quantum way. This means that space and time themselves weren't continuous and smooth, like Einstein imagined, but granular and uncertain, constantly flapping around like microscopic foam. Imagine space-time like a photograph. When you look from far away, it looks smooth and continuous. But if you zoom in trillions of times, getting down to the Planck scale, you'll find that the photo is made of individual pixels, tiny quanta of space and time that are the smallest possible bits of reality. These pixels are constantly blinking in and out of existence, making and breaking tiny curves in the fabric of space-time. This is where revolutionary theories like loop quantum gravity come in, developed by physicists like Lee Smolin and Carlo Rovelli. This theory suggests that space-time isn't a continuous fabric, but rather a network of interconnected loops and nodes, like a mesh woven at a quantum scale. Each loop represents a minimum quantum of area, and each node represents a minimum quantum of volume. The beauty of loop quantum gravity is how it solves some of the deepest problems in cosmology. For example, it suggests that the Big Bang might not have been the true beginning of everything, but rather a big bounce, a grand rebound. According to this theory, our universe might have been born from the collapse of a previous universe that contracted until it hit a maximum density allowed by quantum physics, and then bounced back, expanding again to form the universe we know. It's like a cosmic basketball that hits the floor and bounces back up, except the floor is the granular structure of quantum spacetime itself. This would mean that time didn't start at the Big Bang. It already existed before, in a previous universe. Our Planck era would actually be the moment of the bounce, when one universe transforms into another. Other theories, like string theory, propose that fundamental particles aren't points, but tiny vibrating strings in extra dimensions of space. During the Planck era, these extra dimensions could have played a crucial role in determining the characteristics of our universe. It's like our three-dimensional universe is just a shadow cast by a much richer and more complex reality existing in 10 or 11 dimensions. But here's the frustrating question that keeps physicists up at night. All these theories are extremely tough, maybe impossible, to test experimentally. How do you recreate the conditions of the Planck era in a lab? How do you generate energies trillions of times greater than anything we can produce? It's like trying to study the behavior of oceans using just a cup of water. According to our current understanding, based on the most accepted theories by the scientific community, the Planck era remains an almost insurmountable frontier of human knowledge, but that doesn't mean we should stop trying. Every new discovery, every new experiment, every new astronomical observation brings us a little closer to understanding these crucial first moments of existence. Observatories like the James Webb Space Telescope are letting us look further into space and, therefore, deeper into the past than ever before. Gravitational wave detectors like LIGO might, one day, pick up primordial echoes from those first moments, and increasingly powerful particle accelerators are helping us recreate, on a small scale, the energetic conditions of the early universe. What we know for sure is fascinating. We know that the universe went through an unbelievable transformation in the first moments of its existence. We know that the laws of physics we know today gradually emerged as the cosmos cooled and expanded. We know that matter, energy, space, and time itself were born from this extraordinary process. What we don't know is equally fascinating. We don't know exactly what caused cosmic inflation. We don't know if the Big Bang was really the start of everything, or just a transition between states of the universe. We don't know if there are other dimensions of space beyond the three we experience. We don't know if our universe is unique, or if it is part of an infinite multiverse of parallel realities. And maybe the deepest question of all, we don't know why there is something instead of nothing. Why did the universe bother to exist? Why are the laws of physics exactly as they are, allowing stars to form, planets to pop up, life to evolve, and consciousnesses like ours to emerge and ponder these questions? Cosmic explorers, we've just plunged into the deepest mysteries of existence. We found out there is a lost era of the universe, the Planck Era, where our most fundamental theories about reality just fall apart. We saw how the first second of existence was a period of such dramatic transformations that every trillionth of a second created the conditions for everything we'd come to know. And we explored revolutionary theories like loop quantum gravity, which suggests that space-time itself might have a granular, quantum structure. But maybe the most important discovery is this: our ignorance about the Planck Era isn't a failure of science. It's a humble reminder of the cosmos' sheer magnitude and the extraordinary journey we still have ahead of us. Every unsolved mystery is a door waiting to be opened. Every speculative theory is a map to uncharted territories of knowledge. When we look at the night sky, we read not just seeing distant stars, we re-looking at the direct descendants of those first incomprehensible moments of the universe. The iron in our blood, the calcium in our bones, the oxygen we breathe, all were forged in the cores of stars that were born from the material created in those first cosmic instants. We are, literally, made of stardust that has its origins in the mysteries of the Planck Era. This leads us to a deep thought. If we could emerge from a universe that started so simply, as pure energy in an infinitesimal point, and evolve to the point where we can contemplate our own origins, what other miracles of complexity and beauty are still waiting to be discovered? What other consciousnesses might be looking at their own night skies, asking the same questions about the Planck Era of their own universes? Cosmic explorers, I want to hear from you. What aspect of the Planck Era sparks your curiosity the most? Is it the idea that time and space might be granular? The possibility that our universe is a bounce from a previous universe? Or maybe the exciting prospect that there are still fundamental mysteries waiting to be unraveled? Share your thoughts in the comments. Let us build a discussion that is as rich as the mysteries we explored today. And since we're talking about the frontiers of knowledge, I want to know, what mystery of the universe do you want me to talk about in the next video? Black holes and the information paradox, the search for extraterrestrial life, the dark energy that's speeding up the universe's expansion. Drop your suggestions in the comments, cause our journey of discovery is just getting started. We're on an incredible journey toward 1,000 cosmic explorers, and every one of you who joins our crew makes this adventure richer and more exciting. If this video expanded your cosmic horizons and sparked your curiosity about existence's deepest mysteries, hit subscribe and come be part of our community of universe discoverers. Like this video if it made you think about our intimate connection to the cosmos, and share it with someone else who also marvels at reality's grandeur and mystery. In the next video, we're going to explore another fascinating territory of cosmic frontiers, continuing our mission to make the universe's mysteries understandable and inspiring. Until then, keep looking up at the stars and remember, you are part of the most extraordinary journey ever undertaken, the journey of the universe itself toward consciousness and self-understanding.